So does the second derivative. If you take two derivatives, you're going to see, oh, the entire thing becomes negative. So if you take a second derivative of a cosine, it becomes negative cosine, and you get multiplied by k squared. And also, if you take two derivatives of sine, it becomes negative sine, and you again have a k squared, right? So essentially, the different differential operators seems to be going through these cosine and sine functions without changing their natures much. Okay, an even more succinct description of this is the Fourier representation using using the exponents of imaginary numbers. So another way to represent the Fourier series is to say, okay, I have summation of uk, u hat of k. So this u hat of k is now a complex number, and I have e to the ik of x. So this I is an imaginary number. So e to the ikx is actually equal to cosine of kx plus the imaginary number I times sine of kx. That combination multiplied with an imaginary number itself is going to give you real cosine and real sine terms, right? And this k actually has to go from minus infinity to infinity. Now the derivative is even easier. The derivative to x is equal to the same summation, okay, uk hat times ik times e to the ikx, right? And the second derivative is equal to the same summation uk hat, well, times negative k squared, because I squared is negative 1, e to the same ikx. So the e to the ikx stays there without changing when you take derivatives. And now you probably see where this is going. If I plug this into this differential equation, I actually get rid of all the spatial derivative terms, right? And I only get a ODE for which I can analyze its stability. Okay, so this is for the analytical PDE. We're going to try it on this in the next lecture. And it turns out, if we have a uniform grid spacing, most of actually all the discretization schemes we can think of, finite difference, finite volume, and finite element, have the same properties. If we apply this kind of sinusoidal functions to these numerical schemes, again, we come out with these sinusoidal functions. So again, we can analyze not only the stability of the exact ODE through this kind of Fourier analysis, we can analyze the stability of the numerical discretizations through this kind of Fourier analysis. And we can figure out, for example, why an upwinding gives us additional stability and downwinding destroys stability. And things becomes pretty obvious from a Fourier point of view. And we'll continue next lecture. All right, thank you. Oh, any questions? I'd be happy to stay and answer any questions either regarding this lecture or anything else. Right, I'm glad your phone stayed, didn't die. All right.
Thanks.
Yeah, thank you. See you Wednesday.